Welcome to the Woodlands, Texas, in our applications lab down in Houston. My name is Glenn Williams.
And I'm Thanh Nguyen.
And we are in the XRF applications group. As you can see here, this is right outside our door, right to my left there. And it's where we do everything X-ray here. We're in the X-ray fluorescence group, and that's what we're specializing in, and that's what we're coming to talk to you about today. So there's actually a lot of applications for the pharmaceutical industry using XRF. It's actually surprising there's not more use in the industry. I came from the industry myself, and I wish I had the ability to use an instrument like this before I came here. We can do things like catalyst residues. It's actually a separate talk that we have later today on that. You can look for catalyst poison, so things that are affecting the performance of the catalyst. Salt formation, which is what we're talking about here today, so confirming structure, confirming stoichiometry. And then excipient blend uniformity, we also have a talk about that as well. So I hope you can see a lot of what we're going through. Okay, so as I've mentioned, we're going to be focusing on direct CNOX analysis of solid forms. So what that is confirmation of composition, determining salt stoichiometry, did you form a solvate or a hydrate, and doing this by direct analysis with WD-XRF. As I mentioned, I came from the pharmaceutical industry, worked at Pfizer, Glaxo for about 15 years in total before coming here, and I used to do and make salts in the lab, and one of the things we'd always have to do is confirm the stoichiometry. So we might make a bunch of different materials, do it with different amounts of base or acid and counterion, and then try to figure out what we made. Okay, so salt confirmation was a big deal in order to move forward and figure out do I spend other resources and time in checking the physical properties of this material. So we get this salt form and we want to check stoichiometry. Oftentimes we send this for combustion analysis. Well, if I had this in my lab, it would have been really useful. I wish I had known that this was available, and that was actually available at the time. It's just not widely known in the industry.
Wait, so why use XRF for this technique? A lot of people don't know that it could be very advantageous for this type of analysis. First of all, it's non-destructive, so you can recover your samples back. The sample prep is extremely easy. If you build the method just pouring the powder into a cup, then that's all you need to do for your unknowns. Unlike mass spec, the calibrations are very stable. You do not have to recalibrate every day as long as you maintain the method by drifting it. You can keep it for years. It could be highly quantitative, qualitative as well if you don't have standards. The other thing that I love about the XRF is that it is very repeatable. And you can make your methods ranging from ppms all the way to 100%. Again, you can use it for quality control and also doing research as well.
So XRF is in so many different industries, and we're trying to get it more into the pharmaceutical industry. I mean, this is one area we would like to gain some headway in because it has so many potential uses. I mean, like I said, I wish I had this when I was working. And had this opportunity to use it in so many different ways. But it is in so many industries here. We've all done applications, like done some on food.
Right, so we actually both came from the pharmaceutical industry. So when I first joined this group doing XRF, I didn't realize the many benefits and capabilities that it can do. So like you said, the foods, I did the one for baby foods, and that was quite interesting to see what elements were in there so they can quality control the products, as well as paints, coatings on cars. Metals. Yeah, so yep. And there's a lot of quality control in a lot of products out there that you wouldn't think about, but this is what it's mainly used for, and it's in all these industries that you can think of.
Including money.
Right. We can't talk about that. Right.
Okay, so what is XRF? How does it work? As I said, it's not really widely used in the pharmaceutical industry. So just a quick overview. if you have the opportunity, please come to our workshop, because in the workshop we'll spend more time, discussing, how it works, what are the advantages, disadvantages, and then actually do some prep and calibrations and things. But in a quick, 1-minute summary, what we're doing is we're using X-rays from an X-ray tube to excite the sample, produce fluorescent X-rays in that sample, and there are characteristic X-rays that will be produced depending on what elements are in the material. Essentially what happens is, if the X-rays are of sufficient energy, the primary incident X-rays, they will kick out inner cell electrons. Those will be lost as photoelectrons, and that will leave an unstable state. So the outer cell electrons, which are of higher energy, can fill those voids, and in doing so, they will release a certain amount of energy that will be lost as a fluorescent X-ray. And these are the things that we are, looking to collect and determine what's in a sample, and then how much of those are in the sample. So the intensities are going to be based on the concentration.
As you can see, there's a wide variety of XRF instruments that Rigaku has. There's also more than this that we just can't fit on the screen. However, we're going to distill it down for you for this type of application that we're doing. So we have our fluor models here, which is the 4 kilowatt Primus 4, Primus 4i. The Primus 4 is the tube above configuration, and this one is the tube below. We also carry the Primus 3 Plus, which is just a 3 kilowatt, but it can do pretty much very similar to what these two can, but it's just a little bit lower wattage or power. As well as the Super Mini, which is our benchtop system, is 200 kilowatts, as well as an ED system that's also benchtop. However, we're going to focus on our Primus 4 for this type of application.
And this is ideal for this method. These are what we would say, we think across the board, out of that big list, what we would distill down to say what's good for the pharmaceutical industry. But for various applications, there's certain instruments that we think are better. For this one, it has to be one of these two models, just to do those lighter elements. Okay, so in this particular application, to do the carbon, nitrogen, oxygen analysis, we need to make a quantitative method. And we need to make it with similar, materials that you'll be analyzing. So what we do, like any analytical quantitative method, we need to take a set of standards, so things with known concentrations. Nice thing about this is basically anything you can take off a shelf that's organic, you could prep and run as a standard. So we collect intensities for those different concentrations. We teach the instrument, essentially, and that's building yourself a linear regression or calibration. We then can run unknowns against that and interpolate the results, get the intensity, and get a known or a concentration that we can then use to determine our stoichiometry.
And as I mentioned before, again, we don't do this every time because typically you don't recalibrate an XRF, you just maintain the calibration, and
right.
Just by drifting it or doing check samples.
Yeah, so in the end, after you've set this up, all somebody has to do, it can be really easy to use as a walk-up tool, right. Because you essentially just put it. We'll show this in a few slides. But you just put a little powder in a sample holder and run it on the machine, and you just recall that method and get a result.
Right. So it'd be very advantageous for like an open access facility.
Okay. So what we've done here, this is just an example of calibration we built using essentially expired materials in our lab. So we have a bunch of organic compounds, some of them acids, some of them, actually APIs. And we've taken those and we've normalized those down to carbon, nitrogen, oxygen. So we're taking out hydrogen. So it's normalized without hydrogen, and the reason for that is the X-rays can't see the hydrogen. It's too light of a sample. We can't determine hydrogen in there. But in terms of calculating your stoichiometry, you don't need that. You just need to calculate what the stoichiometry is without hydrogen, and then analyze these samples without hydrogen. And what I would call that is syngas Okay, so if anybody down in, we do some stuff down in South America, and if you go to the convenience store, you have to look for the green cap bottles, unless you want bubbly water every time you drink it. So these are syngas methods.
Okay, then people may not know that. Okay, so how do you prepare the samples? So for this application, what we did is we have this boric acid shell where there's a little divot inside, so that size is about 13 millimeters. You can add anywhere roughly between 50 to 200 milligrams of powder. Again, we don't need to have the exact amount because we're just doing a very light, the carbon, nitrogen, and oxygen, which are very light in energy. So it's just a surface analysis. Once you put the sample in, so there's an aluminum ring here, what you would do is put it in between like we call this a pancake press or any stainless steel dies, and press it down to 15 tons. Once it's pressed, that aluminum ring will basically press everything down and hold that sample in between. The beauty of this is you're not adding in any binder, so the purpose of the boric acid shell or cellulose or whatever matrix that you want to use is it'll hold the sample in, and it's easy for analysis at this point.
And for pretty much all the organics that we've run so far, that's no problem. The nice thing why we recommend this particular instrument that's actually behind Sun right here is this is a tube above instrument. So it's really the only one on the market that can be done like this because we don't need to put any film. We're not risking turning that sample over and having anything that could possibly fall off.
And you can recover the samples.
Right, right. And this is just one example of how we prep it. This is one that works for us. But there are other ways actually to have a rigid solid support, and we can squash that sample in there. But we're using fairly little amounts of material.
So once you prepare it, let's say the calibration is prepared, the sample prep before would be just for anyone who wants to run their unknowns. Once they prepare that sample, you would just come to this simple interface here called the easy analysis. And it's user-friendly where you can just pick your position. Once you pick it, select the methods, and then pretty much hit go. It's as simple as that. And here's like a representative of sample of what it would look like here, right, once you put it in.
This was the actual, like as you saw on that screen, like one of the prep materials. And you can see it's really stable in there. But if there were anything that could kind of crumble off it, no problem, because we're putting it, you know, where the system goes in with the tube above it. So just showing some examples of using those calibrations that we built, just using, you know, expired standards. And I think some of the variation we're seeing here too is because some of these samples are wet. Some of them maybe are supposed to be a hydrate and may have dried out over time, depending on how stable that hydrate was or depending on how hygroscopic some of our samples in the lab are. That's another good benefit to this analysis. You may be getting the right stoichiometry, but it may be hygroscopic material. You'll see that if you run it for combustion analysis. And you would also see something like that similarly here. This is using lactose. So we took a lactose sample, which actually wasn't in our calibration, so we just ran that then against them. And you can see the result against theory, again, normalized without hydrogen. But we know right away that there's it's not a hydrated form, it's not a solvate, and well, we can't really form a salt of that. If we could, you would see if that had been formed or not. As well as aspirin. Again, here's theory for the aspirin on carbon and oxygen, and it matches quite nicely. And that was about under a 10-minute analysis time, depending on how much sample we can put in, and you know, and how long we need to count, how many elements. We can keep these methods probably within 5 to 10 minutes long.
Yes, so now with this, what we're showing here is, let's say you have less than 50 milligrams. So a lot of groups, we've been approached by a lot of groups who have less than that. What do you do? So there are other options here with these shells here that are different in diameter. So typically the 5 millimeter diameter, you can hold about 10 to 50. If you need to, you can go to the smaller one. However, you would need to obviously build a calibration with these sizes. But there are options out there, and the sample prep is the same as what was shown before.
Yeah, in fact, what we can do is if you build a calibration with, say, the bigger size, all you have to do is keep the standards in the system and then just recollect that method really quickly with each of the other diaphragm sizes that the system can run. And then you're creating all your methods at one time, but you can decide at which point you want to use the smaller or the larger samples.
Right. So there are options out there. You know, you're not limited to the 50 or 200 milligram options.
And this is just an example. We did that. So we did the same samples, but now we're running a 3 millimeter measurement area. So there's a diaphragm in the system that you have the option with. You can go to a 3. We can configure the systems in different ways, but we can do down to a 500 micron spot size. You wouldn't want to be doing the carbon, nitrogen, oxygen analysis with that. But at 3 millimeters, 10, and then up, we can, get data no problem with these. So this is just an example. And we have a couple that we've excluded from the curves. And some of these, I think this one was like lysine, and we just determined that it was, it was a hydrate. So that's why. And if we actually recalculate it that way, it would fit. Okay, so we've established the carbon, nitrogen, oxygen part, but what about adding other atoms, the X here, right? So if I have something like a atorvastatin, I might have a fluorine in the molecule, maybe I have compounds with sulfur groups, and of course the counterion. The counterion may be a metal or maybe another organic acid. But if I want to add these other elements to the method, I want to be able to look for those as well and see, did I make a mono calcium salt? Did I make a hydrate? What did I actually make? So when I'm adding, the API in solution to a counterion solution, I get a precipitation. What is that precipitation? Before I go on and do other work and, explore, the thermal properties, hygroscopicity, all these kind of things, crystallinity, I want to see first, did I make something that's useful? Okay. So essentially what we do here, okay, so we have the carbon, nitrogen, oxygen method, and we just talked about adding these other atoms. How do I do that? How to do other elements to the actual method? I don't necessarily have a whole bunch of standards to do this, and so that's the beauty of this and this software is that, okay, I've established carbon, nitrogen, oxygen calibrations. Those are going to be my harder ones to analyze, so I really need to get those right. The system comes with a library built in. So what I can do is I can easily just add elements. So let's, in this case, I added sulfur, chlorine, and now I'm going to add a phosphorus. And what I do is I just add that to the list, and then I go in and I change the type here to library. So what private means is you have your own private set of standards. You're doing a calibration. Library means there's a library built in, and there's actually a library built in with carbon, nitrogen, and oxygen, but it's not going to be as accurate as what we're going to do here. So we keep those ones as private. You have that calibration, and at any point you can go and copy the method and just add library elements in. You might ask, well, how come I don't just do that for every single element? Well, in general, you know what you're looking for. You can do that. It just makes the method longer. So the nice thing here is I can just duplicate the method and say, hey, I want to add these 3 or 4 library elements in. It'll add another minute or 2 to the method, and then you get your result.
But you don't have to recalibrate the carbon, nitrogen, oxygen again, because you copy the method and now you're just adding in the other elements and use the library. So that's really nice with the software feature.
And once I do that, it's saved. So the next time somebody wants to run and do carbon, nitrogen, oxygen with sulfur, chlorine, and phosphorus, you might decide you always want to have sulfur in there. You always want to have chlorine, just for the cases that you have compounds with those elements. So I've done that. I've got my new method that I made in about a minute or 2. Saved method now that I can use at any point. And now I can just set up a sample queue as we showed before, but I don't have to have the same methods on the system. So in other words, I don't have to run all the same method. I'm going to set up a batch of samples. I can use sample 1 could be one method just for carbon, nitrogen, oxygen, be a faster analysis, and then 2 could have sulfur added to it. 3 could have sulfur, chlorine, and phosphorus. So it just depends on how we want to do it. Okay. So in the case of the atorvastatin that we were showing, we're trying to make a calcium salt. This would be theory for atorvastatin calcium, based on, again, normalized without hydrogen. And this would be our theoretical mass percents for the calcium salt. We've then done that. We added calcium and fluorine to the method, and we ran a sample. Well, lo and behold, it doesn't really match very well, especially with the element that we're really looking for to see the stoichiometry was calcium. Well, I'm seeing it's almost half. All I have to do is then recalculate what my stoichiometry would be for a hemicalcium salt. And as you can see here, now even our carbon, nitrogen, and oxygen numbers are matching, and most importantly, our calcium is showing a hemicalcium salt. So in a matter of just a couple minutes, I'm able to put a sample on, go and check my stoichiometry, and verify I haven't done any chemistry on the actual compound. So that's pretty much to give you a flavor for how we would do this. We're certainly more than happy if you have individual questions to contact us. Our emails are on here. You can go back to these presentations at any point. I know they're going to be posted for a long time. Go to some of our other sessions. But if you can, more importantly, if you can go and join us right up here, our XRF workshop at 2:30, we're going to cover a lot of the stuff, how we do the calibrations, how we run samples. We'll show you actually putting samples in, show you how the machine runs them and everything. So
yeah, and also if you have direct questions about your products from your company, you can, again, feel free to email us with any questions, and we'll be happy to answer you. All right.
Thanks for joining us.